Hello students, welcome to class 12 physics. In this video we are going to discuss about the resonance of LCR series circuit of chapter 7 alternating current. So first of all, let us understand what is resonance. A phenomena in which an external force or a vibrating system forces another system around it to vibrate with greater amplitude at a specified frequency of operation is called resonance. Example, let the phenomena is a child on a swing. The swing has a natural frequency for swinging back and forth. If the child pulls on the rope at regular intervals and the frequency of the pulse is almost the same as the frequency of the swinging, the amplitude of the swinging will be larger. A swing cannot stop. This is called resonance. So, in short, it is nothing but it is the event to get the maximum amplitude, or we can say maximum amplitude of the oscillations. So students, you may note down this definition with the example. Now explain resonance for an LCR series circuit and write its uses. In what kind of circuit will it be possible? Now see, as we have already discussed, resonance is nothing but to get the maximum amplitude for the oscillations. That is an event to get the maximum amplitude. So here we are talking about the resonance for an LCR series circuit. So here we can say that it is the event for which we will be getting the maximum current. So for an LCR series circuit driven with voltage of amplitude Vm and frequency omega, the current amplitude is given by Im is equals to Vm by Z. Because in this LCR series circuit, we are having resistance as well as the reactances. So by applying the Ohm's law, we will be getting I equals to V upon Z, where Z is nothing but the impedance. And impedance is resistance plus reactance. And Z is equal to under root of R square plus Xc minus XL whole square. So rewriting this equation, we get Vm upon under root R square plus Xc minus XL whole square. Here Xc is the capacitive reactance, which is equals to 1 upon omega C, and XL is inductive reactance, which is equals to omega L. So substituting the formula of Xc and XL in the above equation, we get Im equals to Vm upon under root R square plus, instead of Xc we will be writing its formula as 1 upon omega C, minus, instead of XL in the above equation we will be writing it as omega L. So 1 upon omega C minus omega L whole square. Hence, if omega is varied, so current amplitude is varied at a particular frequency omega 0. X equals to XL and the impedance is minimum. So here, what we desire is the maximum current, because resonance is nothing but it is an event to get the maximum amplitude or maximum current. So we here by this equation we get the maximum value of the current when this value Z is as small as possible. If this Z is minimum, then Im value will be maximum. So the Z value should be minimum. That means these whole term should be as small as possible. For that, we can take these two terms as equal so that this whole term becomes 0. So we can say 1 upon omega C is equals to omega L, so that when we take the difference, its value will be 0, and in the denominator we will be getting just R. So 1 upon omega C equals to omega L, or we can write it as Xc equals to XL. So when we write this, we get Im equals to Vm upon R, because now Z is equals to R. The value of the amplitude of current is maximum. This is called the resonance. Therefore, if Xc is equals to XL, then from equation 1, Im equals to Vm upon R. At resonant frequency, amplitude is maximum and Xc equals to XL. So this is the condition for the resonance, that the capacitive reactance should be equal to the inductive reactance. Or we can say 1 upon omega 0 C is equals to omega 0 L. Now, taking omega 0 on the other side, it will be omega 0 square, and taking L on the other side, it will be 1 upon LC. Taking square root on both the sides, it will be omega 0 equals to 1 upon root LC. Hence, at resonant frequency, amplitude of current becomes maximum, and it is Im equals to Vm by R. Resonant circuits have a variety of applications, for example in the tuning mechanism of a radio or a TV set. You might have experienced that when you tune the radio, then when reaching the particular station, there will be noise. Why? Because the range of frequencies is greater. But when you reach the particular frequency, at that the voice quality will be more better. The antenna of a radio accepts signals from many broadcasting stations. The signal picked up in the antenna acts as a source in the tuning circuit of the radio, so the circuit can be driven at many frequencies. But to hear one particular radio station, we tune the radio. In tuning, we vary the capacitance of a capacitor in the tuning circuit such that the resonant frequency of the circuit becomes nearly equal to the frequency of the radio signal received. Hence, resonance occurs and the amplitude of the current becomes maximum. So, for tuning the particular station, the current should be maximum, and the current becomes maximum when the antenna's frequency and the frequency of the channel that is matching. If it is same, then the current will be maximum. If the current is maximum, then the resonance condition is satisfied and the voice quality will be better. The resonance phenomena is exhibited by a circuit only if both L and C are present in the circuit, because this LC circuit is also termed as the oscillator circuit or the tuned circuit, which is used to tune the particular frequency. Only then do the voltages across L and C cancel each other, and the current amplitude is Im equals to Vm by R, the total source voltage appearing across R. This means that we cannot have resonance in an RL and RC circuit, but resonance L and C both should be in the circuit. So to satisfy this condition, the resonance condition, one should use the LC circuit. You can see this resonance curve. If the curve is narrow, then the voice quality will be better compared to that which is having the broader curve. So students, you may note down this theory. Now let us obtain an equation for sharpness of resonance in an LCR series circuit. And what is quality factor Q? Next explain bandwidth. The amplitude of the current in the series LCR circuit is Im equals to Vm upon Z, that is Vm upon under root R square plus Xc minus XL whole square. When we take omega equals to omega 0, that is equals to 1 upon root LC, amplitude of the current is maximum. This maximum amplitude is Im equals to Vm by R, that we have already seen in the previous theory. For the values of omega other than omega 0, the amplitude of the current is less than the maximum value. Values of omega for which the current amplitude is 1 by root 2 times its maximum value. At this value, the power dissipated by the circuit becomes half. If I equals to Im by root 2, power becomes half, and two values of omega is obtained according to as given figure. Variation of Im with omega for two cases: R equals to 100 ohm, R equals to 200 ohm, L equals to 100 millihenry. There are two such values of omega, say omega 1 and omega 2, one greater and other smaller than omega 0, and symmetrical about omega 0. So from this we can write omega 1 equals to omega 0 plus delta omega, and omega 2 equals to omega 0 minus delta omega. Taking the difference of these two frequencies, that is omega 1 minus omega 2, it becomes 2 delta omega. From this equation, from these two equations, on the left hand side it will be omega 1 minus omega 2. For the right hand equation, it becomes omega 0 plus delta omega minus omega 0. Here it is minus, so minus minus plus delta omega. This gets cancelled. We will be having 2 delta omega. So the difference omega 1 minus omega 2 equals to 2 delta omega is called the bandwidth of the circuit. The quantity omega 0 upon 2 delta omega is regarded as the measure of the sharpness of resonance. The smaller the delta omega, the sharper or narrower is the resonance. That means the bandwidth should be as small as possible, so the curve will be narrow. And if the curve is narrow, that is the resonance is narrow, then the voice quality will be better. So students, you may note down this theory.